discuss climate change in California. And what I'm going to do is show you some analysis of historical climate change, that is climate change in the 20th century. I'll show you how especially temperatures have changed and offer some hypotheses about why. And then turn to the future and show you future projected changes in temperature and precipitation and other variables in California. I'll illustrate uncertainties in those projections, discuss where those uncertainties come from, and then I'll spend about 10 minutes talking about societal impacts. By societal impacts, I mean impacts of climate change, changes in temperature, and so on things that actually we care about, like water availability, air quality, agriculture, and so on. And that will serve as a bridge to many of the future talks in the series, which will focus in more depth on several of those potential societal impacts. Okay, so starting with historical temperature trends in California. First, why do we look at historical temperature trends? I mean, really what we're focused on here is future climate change in California and understanding what we need to do to prepare for it. Well, obviously, our confidence in predicting future trends is increased if we can show that we understand historical climate trends. And as I'll show you, we understand them to some extent, but there's important aspects we don't understand. The other thing for people like me is that looking at historical climate trends really does improve your understanding of what's going on, that is, the factors that influence climate on a regional scale. And as I'll show you, it's actually fairly complicated, and there's more going on than you might think. So I'm going to just start by showing you historical trends in temperature. And actually, for purposes of studying history, I'm mostly going to focus on temperature. And the reason is that temperature is, for one thing, a very well-observed variable, and for another thing, temperature, of course, has societal impact. The other quantity that's very important is precipitation. Fortunately, precipitation is really harder to analyze because, as you know, if you've lived here for more than a few years, there's tremendous natural variability in precipitation amounts from month to month and year to year. I mean, this month was tremendously wet. Last month was tremendously dry. We have wet years and dry years. And some of that is explainable. Some of that is due to El Nino and La Nina, for example. But a lot of it is just random. And so with precipitation, it is actually difficult, although not impossible, to see slow trends. And the reason, again, is there's just so much natural variation. Okay, so these are observed trends in temperature during the latter half of the 20th century. I'm showing you, actually I'm going to show you summer, and then I'm going to pop those up. But for now, this is winter trends in temperature. The top panel is what I call daytime temperatures, but it's really the maximum temperature recorded during any 24-hour period. Okay, I refer to that as daytime temperatures. The bottom panel is what I call nighttime temperatures, but strictly speaking, it's the lowest temperature recorded during any 24-hour period. The green contour is basically the outline of the Central Valley. It's not really relevant for this discussion. These dots are locations of certain observing stations, also not really relevant. What is relevant is that, well, in regions where it's gray, actually it looks white from where I'm sitting, but in those regions there's no statistically significant trend, so I haven't shown it. What you see, I hope, is most of the state is experienced warming. Most of these maps are red. That means we've seen warming. It looks, and it's true, that there has been apparently more warming in nighttime than in daytime, which is interesting and not fully understood. I should say that this is one observational data set. If you look at others, which I've done, it looks generally similar. Okay, so this seems to be a robust result. There's been warming in winter, more warming at night than in daytime. If we look in summer, actually it's quite different, and it may be a bit surprising to you, and I hope you can see the color, that there really has been, essentially in daytime in summer, no warming. And that was a surprise to me. There has been warming at nighttime in summer. That's also, I think, very interesting because that's consistent with my anecdotal experience. I mean, I've lived here for almost 30 years, and my memory is that, it used to really cool down at night, and it doesn't seem to anymore. And, I have to say, generally, I'm suspicious of anecdotal anecdotal evidence about climate change. I mean, old timers say blah blah blah. It used to snow. I typically don't buy that, but in this case, my own anecdotal experience is consistent with the rigorous observations, which do show warming at night in summer. So what I'm showing you is it's warm generally, more warming at night than in daytime, more warming in winter than in summer. And as I'll show you, we understand some of that, but not all of it. I want to show you some trends in other climatic variables. And I'll show you, I think, a consistent picture of warming and impacts of warming on the hydrological cycle. These are also trends over the latter half of the 20th century. These are trends in snow water content, the snowpack over the west. And blue means there's actually more snow. Red means there's actually less snow. And what you see is in most of the western U.S., a reduction in snow. In parts of the southern west, there's actually more snow. And I'll show you actually that the increases in snow, and this is snow on the ground, not snowfall, the increases in snow occur in regions where there's more precipitation. This is trends in precipitation. In the southern part of the west, there's been more precipitation, consistent with there being more snow. In most of the regions where there's less snow, there's actually no significant trend in. So the interpretation is that the reduction in snow is a consequence of warming. This is another warming-related result, and it's a very important one. And this has to do with the seasonal timing of river flows. Okay, and we care about this mainly because of our water supply, and our water supply depends on late-season flow, which mostly comes from snowmelt and fills the reservoirs after it's not raining anymore. Okay, and what this is showing is that river flow is tending to come earlier here. And what's actually shown is the trend again on 50 years, the so-called center timing date. And the center timing date is the date at which half of, if you have a measuring station somewhere on a river, the date at which half the annual flow has gone by. Okay, so obviously that's something you only know at the end of the water year. You don't know it at the moment it happens. But it's a good measure of when in the year is the river flow coming. And the predominance of red circles is telling you these are on so-called snow-dominated watersheds, that on snow-dominated watersheds, river flow is coming earlier in the year. Okay, this is the same thing on lower elevation watersheds that aren't snow-dominated. You don't see that tendency earlier in the year flows. So again, what this is telling you is that the earlier in the year river flows is not a result of some change in the timing of precipitation. It's a result of warming, and specifically a shift in the form of precipitation away from snow towards rain, also a tendency for what snow there is to melt earlier. So we've seen this in the observations, and we expect this trend to increase. Sea level is also rising. Sea level has risen steadily, actually since the beginning of the 19th century. It hasn't risen much. This is showing sea level rise at 3 different locations in the west, sort of more or less 7 inches about 1930. So that's not dramatic, but it's likely that sea level rise will accelerate, as I'll show you. And the reason for that is Greenland. Okay, and it's interesting that a place as far away as Greenland is potentially very important to our future. But what we see in Greenland, well, the issue with Greenland and Antarctica also is huge land ice sheet, and if all of that ice on Greenland melt, raise sea level by 7 meters, about 21 feet. Now, that's not going to happen immediately, but the point is that the potential for sea level rise from melting of Greenland is huge. Antarctica has actually got much more ice than that, but Antarctica for the moment seems to be stable. What this is showing is trends over just a few years showing apparent loss of mass Greenland ice sheet, and that's actually measured a couple different ways from satellites. One is from gravity anomalies, and the other is from actual just altimetry, which tells you basically the volume of the ice sheet. The other thing that's happening is they have seismometers on Greenland, and these green bars are measuring the frequency of what they call ice quakes, which is large-scale motions of the ice, and they're picked up by seismometers. The gray bars are actually earthquakes. So earthquakes aren't increasing, but ice quakes are increasing, suggesting that things are starting to shift in a sort of an ominous way. This is the last slide I'm going to show you on observations, and this is reconstruction of a river flow. And I got to be honest, I don't remember where the river is, but this is from work by a guy named Scott Stein at what used to be called Cal State Hayward, now Cal State East Bay. But what he's shown is that in the Middle Ages, in many regions of the West, there were these really prolonged, very severe droughts. And again, this is a reconstruction of river flow, and he's showing, and you probably can't read this, 80, 1,000, 80, 1,200, these droughts that lasted, centuries. So this is just a reminder that the sort of friendly climate regime that we're in now, or at least maybe you don't think it's friendly, but at least we're used to it, hasn't always been there, and may not always been there in the future. Okay, so that's sort of a quickie tour of climate change during the 20th century. Now the issue is, okay, what do we think has caused these trends? And I'll show you some of these trends we understand, some actually we don't. It's actually, I think, quite interesting, so I hope I won't talk too long. This is, I think, partly recapping what I've shown you in terms of temperature trends. So the color here illustrates temperature trends, so more red is more warming. So this is night, this is day, this is winter, this is summer. Okay, so I showed you in summer, at daytime, there's really no warming. And there's more warming in winter than summer. There's more warming at night day. So why would that be? Well, as I'll show you, I think the underlying warming is actually greenhouse warming. And I did a study that showed apparently that we're seeing warming trends that are too rapid to be natural. It's in California. It's been shown on larger scales repeatedly that the warming is too rapid to be entirely natural. It's consistent with greenhouse warming. So it walks like a duck, it quacks like a duck. It's probably greenhouse warming. Now, what's interesting, for example, in summer and daytime, where we see really no trend, actually, I think that's the most interesting result of all. And my interpretation of that is not that nothing's happening. I think actually what's happening is canceling things. I think there's greenhouse warming, and clearly there are cooling influences. Irrigation is one, and particulate pollution is another, which are, I think, canceling the greenhouse warming. The issue of why more warming at night than in day is not entirely understood, but one contributing factor clearly is particulates, aerosols. Particulates are complex in terms of how they affect climate, but the dominant effect seems to be cooling, and the cooling mechanism is reflection of sunlight. Okay, so that operates primarily in daytime, obviously, when there is sunlight. The other factor that could contribute to more warming at night is an increase in low cloud. This hasn't been seen in California, but the observations aren't good enough. But if you did have an increase in low cloud cools in the daytime, again, by reflecting sunlight. It warms at night by acting as a blanket. So an increase in low cloud would tend to give you this effect of more warming in night than in day. And by the way, that's seen essentially everywhere, not just in California. The other factor I'll show you is that in summer and daytime, irrigation has clearly acted to cool the climate. I think that's very interesting. So what I'm going to do first is show you some evidence for why I'm arguing that the underlying warming trend is probably greenhouse warming. And this cartoon says, I don't know anything about global warming, but these ice cubes are melting like crazy. Okay. Now the point of the cartoon, aside from the fact that it's less boring than science, is that just because you see a trend doesn't mean it's due to humans. Okay. Climate varies naturally for all kinds of reasons and all kinds of timescales. Just to underscore that, this is a temperature reconstruction. I don't know if you can read the scale. This is going back 400,000 years. Temperature changes on Greenland. Okay, these are huge changes, have a huge amount of statistical significance. They have nothing to do with humans. It's ice ages coming and going. So climate can change for natural reasons as well as human reasons. So just because we see a trend doesn't mean it's human. The issue of seeing any kind of a trend is difficult, and it's more difficult, and this is what this slide is trying to illustrate. It's more difficult if you look on a smaller region, and the reason it's more difficult is when you're looking for a slow trend, you have to pick it out of the noise of natural climate variability. Okay, and this is showing in the top panel on a global scale. This is sort of the noise. The blue is sort of the noise of climate variability. The red curve, these are model simulations. The red curve is a temperature plot that has natural variability, but also a trend in it. And you can see on a global scale, trend is bigger than the noise, and so you can see, if you can give it sort of as a signal to noise problem, you can actually see the signal bigger than the noise. The problem is, as you look at smaller and smaller scales, signal actually is about the same, and the noise of variability gets much, much, much bigger. So looking for a signal of human influences on the scale of California, which is what I did in the study I just finished, is actually it's difficult because this noise tends to be very large. So this is just quickly illustrating the result. And what we did is we simply compared observed trends during the latter half of the what we think is the maximum likely trend due to natural variability. So these cryptic names are names of different observational data sets. These dots show the temperature trend during the latter half of the 20th century from each of these 4 different data sets. They don't completely agree, but they all show warming. This one shows less warming than the others. This is the uncertainty in the trend. These dotted lines are estimates of what we think is the maximum likely temperature trend on a timescale of 50 years from natural climate variability. Okay, and that seems to be smaller than observed trend. Okay, implying that the observed trend is probably not due entirely to natural phenomena. So there must be something else going on. The obvious culprit is greenhouse warming. Now this happens to be this result happens to pertain to the annual average of daily minimum temperature. That's nighttime warming in all seasons of the year, which I showed you. Nighttime warming is increasing very rapidly, and in that case, we do see it seems to be too rapid to be entirely natural. This is the same sort of analysis, more finely divided. Okay, we looked annual. We looked in the 4 seasons. We looked at daily average temperatures, daily minimum temperatures, daily maximum temperatures, and the so-called diurnal temperature range. Essentially, what I'm showing you is that, well, as I showed you before, again, these dots are the observed trends. The observed trends at night are greater than the observed trends in daytime. The observed trends at nighttime, in general, seem to be too rapid to be entirely natural. The observed trends in the daytime are within the bounds of natural variability. And again, that doesn't necessarily mean nothing's going on, but if there is greenhouse warming, it's being canceled by other factors, which I think are probably particulates and to some extent irrigation. Okay, so the message from this is that some of the temperature trends that we see seem to be too rapid to be natural. Others are within the bounds of natural variability. I've mentioned irrigation a couple of times. And it's interesting, actually, that irrigation in California seems to have a very, very significant influence on climate. And of course, because it's irrigation, well, why would that be? Well, irrigation keeps the surface wet. And if the surface is wet, there's going to be more evaporation. That's a very simple mechanism. It's the mechanism behind swamp coolers. Used to be used and are now being used more to cool buildings. It's a mechanism. That's why perspiration works. It's because a wet surface, you get more evaporation, you get cooling. So if that's what's going on, you would expect the effect of irrigation to occur, first of all, in summer, which is when irrigation is practiced, and also in daytime when the sun is out, okay, and when most of the evaporation occurs. And that seems to be the case. Now, what I'm showing you here is the results from an observational study done by a couple of colleagues, Celine Bonfils and David Lobel. And I think they did a really nice job of just isolating the effect of irrigation temperature in California. And what they did is they looked at low elevation regions. I don't want to confuse things by looking in the mountains where there's all kinds of different. They looked at low elevation regions. They divided those regions into 50-kilometer squares, and they characterized each square by the fraction that's irrigated fraction. That's what's shown on this axis. And then what they did is they looked at the temperature trend again, on 50 years in each of those squares. Okay, and what's shown on this vertical axis is actually not the temperature trend exactly, but it's the difference in the temperature trend in regions that are heavily irrigated. Difference in trend in heavily irrigated regions that experience essentially no irrigation. But the idea is to isolate effects of increasing irrigation on temperature trends. The 4 panels, they looked at 4 different observational data sets for redundancy. But this one is, I think, the cleanest results all illustrated here. The green is a result in summer. Okay, so what is this saying? This is saying in summer, heavily irrigated regions have less of a warming trend, more of a cooling trend. Lightly irrigated regions. This blue, which is hard to see from my angle, is in winter. And in winter, there's essentially no effect of irrigation on temperature trend, which is what you'd expect because there is essentially no irrigation in winter. Now, again, this pertains to daily maximum temperatures. Okay, so that's saying in daytime, irrigation seems to act as a cooling influence. This is the same analysis done for nighttime temperatures. And what you see for nighttime temperatures is irrigation seems to have no effect. Okay, and that's exactly what you expect. So what this is showing is that irrigation seems to be a cooling influence, and it seems to be a cooling influence in summer in daytime. Those are observations. These are model simulations of effects of irrigation. These are a little crude in the sense that the way irrigation is represented in the model is the surface is forced to be very wet. It probably overestimates the effect of irrigation, but nonetheless, the point is that the effects are potentially large, and you can see in these irrigated regions, the effect on the daily average temperature in August is several degrees. The effect on the daily maximum temperature in August is even larger than that. Again, this is probably an overestimate, but the point is locally, the effects of irrigation are potentially very large. The other thing I should say is that these models are consistent with the observations in that they show the effect of irrigation is primarily in summer and primarily in daytime. I mentioned particulates a couple of times. There's no question that on a global scale, particulates are very important. They're hard to represent in models, both because the physics is complicated and also because we simply don't know. I mean, particulates come from all sorts of sources. For example, in the Central Valley, agriculture stirs up a lot of dust. Do we have good observations of that? No. We suspect that it's an important cooling influence. This is an article, I don't know if you can read the headline, but it says, strong present-day aerosol cooling implies a hot future. Okay, that's an important point, is that we've, I think, been spared a lot of greenhouse warming up to now by the cooling influence of particulates. As we continue to clean up the air, which is a good thing, we're going to experience more warming. Okay, so again, to recap this, I think what's going on with temperature trends is I think there's an underlying greenhouse warming. I think clearly irrigation is tending to cause cooling in daytime and summer. Particulates, I think, also are contributing to cooling in the daytime, and that explains, at least partially, why we see this sort of complex pattern of warming trends. Before I go on to showing you the future, I want to make the point, actually, that if you look at global climate models, they don't really explain all this complex richness in historical temperature trends. I'll try to illustrate this here. This axis shows summer trends in California. This axis shows winter temperature trends in California. The gray dots are models, the black dots are observations. So what this is telling us is actually the models do okay in terms of explaining summer trends. They don't do okay. They actually underpredict trends in winter, and this is nighttime. So in winter, we're seeing actually more warming at night than we would expect from models. In summer, as you might expect, in summer, the models, which again are the gray, predict some significant warming. We really don't see that. So the point is that these global climate models don't explain very well the historical warming. Now, I'm not entirely surprised by that. I'm not entirely surprised by that because, for one thing, these are very coarse models. I think you'd be shocked if you saw how coarse they are. They don't include a lot of topographic detail. They don't have snow, for example. Mountains are too low. So you wouldn't. There's a lot of regional climate you wouldn't expect them to capture. The other thing that's important is a lot of the factors that do influence climate simply aren't represented in these coarse scale global models. They are represented in finer scale regional models. But in particular, land use change, simply not there. Irrigation, which I showed you is important, is simply not there. The aerosols, some types are there, many types aren't there. I mentioned there's no snow. The snow is a very important climatic influence. That's not there either. So there's reasons why these models won't explain a lot of the complex regional climate history. Having said that, I'm now going to show you projections from those very same models of what's going to happen in the future. Now, did I just undercut the rest of my talk? Well, not exactly. And the reason is, as I said at the beginning, I really think that you can make an argument, and I actually almost believe this argument. I think that the future is going to be simpler than the past. And this is trying to illustrate that. This is the left. People tell me this is laws of Euclid, but anyway, okay, on the left, the 20th century. On the right is the 21st century. And these squares represent different factors influencing climate. Okay, so this is CO2, really greenhouse gases, urbanization, aerosols, and irrigation. And factors above the line tend to cause warming. Factors below the line tend to cause. Okay. So what I showed you in the 20th century, there's actually a lot going on. There seems to be greenhouse warming. There, I think, clearly is urbanization, which is also a warming influence, but less important than greenhouse warming. Aerosols are a cooling influence. Irrigation is a cooling influence. They cancel. They tend to cancel. They don't cancel uniformly because irrigation, for example, is more important in summer than winter and so on. So the point is, in the 20th century, there's warming things going on. There's cooling things going on. There's some cancellation. It's actually pretty complicated. The 21st century, in all likelihood, is going to be simpler. And one reason is, of course, there's going to be more greenhouse gases in the atmosphere. So that's a big warming influence. There's going to be more urbanization, clearly. That's another warming influence, although much less important. Aerosols are going to decrease more as we continue to clean up air quality. Good thing. Irrigation also clearly is going to decrease, and part of that is simply, the paving of the Central Valley. And the other part of it is, as we continue to have water shortages, and those are going to get worse, irrigation, to the extent that it's practiced, is going to have to be practiced in a manner that's more economical with water. We're going to have to be more careful with how we use water. So for those reasons, I think it's clear that these cooling factors are going to become less important. So I think the 21st century, what I'm saying is greenhouse warming is going to be the dominant climate influence. And in a way that's bad because it's harmful, but for people like me, it's actually nice because it's, of all of these, it's the one that we actually understand best. Okay, so let me show you future trends. These are temperature trends. These are obviously from models, since we're dealing with the future. This goes out to basically 2100. There's a whole lot of spaghetti here. And why the spaghetti? Well, the spaghetti is because I'm showing you results, 15 different climate models, and they don't all agree, unfortunately. And also, I'm showing you results for 3 different, what we call greenhouse gas emission scenarios. That's an important concept. Court mentioned this last week, but, the major driver of climate change is the buildup of greenhouse gases in the atmosphere. Now, how rapid is that going to be? Well, we don't know, and we can't know because it depends on all kinds of decisions made by all kinds of people. It depends on whether you buy a Toyota Tundra or a Prius. It depends on how well we implement AB 32. It depends on what happens in China and India. So we can't possibly know how rapidly greenhouse gases will build up in the atmosphere. So we have scenarios, which mean guesses. Okay. And actually, it's interesting to me that there's a huge cottage industry of people who spend untold amounts of money and effort producing these guesses, which you just draw a line on a curve. It seems just as good. But so part of this uncertainty, roughly half of this uncertainty in future warming, is we don't know how rapid the greenhouse. We don't know, and we can't know. Roughly half of the uncertainty is different models give different answers, and that is a problem. And that's something we can and should do something about. But for the moment, we have uncertainty. But notice, despite uncertainty, this is the historical warming. This is, again, all in California now. This is the historical warming on the same scale. It looks pretty small, okay? So, and also notice the scale here. This is 2 degrees. Now, these are degrees C, okay? So you got to multiply by 9 over 5. So that's still, it's 3.5. This is, 5 or 6 degrees C, so that's, sort of 10 degrees Fahrenheit. So actually, first of all, 2 points. One is, whether we end up here, it's a big difference from ending up here, okay? This is really, I think, completely unacceptable. This is probably intolerable. But the other point is that all of this is much more warming than we've already experienced. So it seems like it's going to get much worse. The question is how much. Those are trends in temperature. For precipitation, so this is the plot I just showed you in the previous. This is precipitation. Okay, that's a real Philo Linguini. Okay, and what that's telling you, this is the 0 line. Okay, so what that's telling you is we don't know if it's going to get wetter or dry. Actually, there's more Linguini below here than above, I think. But basically, lot of the impact on the water supply actually don't care about this. What they care about is warming, and the reason they care about warming is warming melts the snow. You really need the snow. Okay. Now the reason for that, I got to show you. I mean, the reason for that, this complete uncertainty, is an accident of geography, and the accident of geography, and this is showing you from the same models temperature trends on a larger scale. Okay, and what I'm showing you, it's hard to see the colors here, but the models agree that the high latitudes are going to get wetter. They agree that the subtropics are going to get drier. This is the zero line, line of zero predicted change. And this is an average. This result is an average of 18 models. Okay. Notice that the line of zero precipitation change goes through much of the U.S., including California. So we seem to be right on a border between a region that's going to get wetter in the north and drier in the south. And the reason for the big bowl of spaghetti is that some models put that border towards the bottom of California, and some put it towards it. So it really depends on where that line of zero change happens to fall in California, and that's very hard to predict. So I'm actually, honestly, not optimistic about reducing this uncertainty. I think it's very tough. I used to be optimistic, but then I learned something. The other thing I want to mention is sea level, and you know the key issue, really, well, one issue with sea level is Greenland melting, and we've up until a couple of years ago, we assumed that was way in the future. All of a sudden, it seems like maybe it's not way in the future. That introduces a lot more uncertainty into sea level rise than we thought. And actually, interestingly, the sort of the stated uncertainty or the recognized uncertainty now, sea level rise is much greater than it was a couple of years ago, because all of a sudden we realize, hey, Greenland might be melting. Holy cow! Okay. Now the other thing with sea level rise is the excursions. Okay, that is the short timescale variations about the mean, and of course that's the first thing that gets you. You know, as sea level slowly rises, what happens is one stormy day, some big wave comes into your living room. Now this is illustrating how that works. This is actually from a study that assumed a pretty modest rise global sea level, 30 centimeters by 2100. That's really at the low end of the range, actually. Okay. And this is a projection of sea level rise in the delta, of course. Now, I think all of you understand the importance of sea level rise in the delta. We want to keep the salt water out of the delta because, our drinking water, for no good reason, really percolates through the delta. And so if it gets salty, that's a big problem. And so what we're showing is the projected hours per year where the water level in the delta is above the historical 99.99 part in 10,000. That's a sea level that occurs about 1 hour a year. Okay, so in the future, you can see that these excursions occur more and more often. By 2100, again, this is with a modest increase in sea level rise. These excursions occur 500 or 600 hours a year, 500 or 600 times more often than they occur now. Now these excursions, I should say, are due to the usual factors that cause the sea level to bump up. One of those is El Nino. Storms cause low atmospheric pressure, which cause sea level to bump up. Storms also cause wind, which causes sea level to bump up. I should also mention that the delta is actually quite protected because it's inland. It's actually quite protected from short fluctuations in sea level. It's worse if you look on the coast. This is actually interesting. The red curve is interesting. And the point of the red curve is that water levels in the delta, remember, delta is an estuary, so sea level is one influencing factor, and river input is another influencing factor. And what happens is you can get a double whammy. If there's stormy weather, sea level tends to rise. But you also tend to get a lot of precipitation, and quickly that precipitation turns into river flow. So you get higher sea levels tending to cause water levels to go up in the delta, and you also get enhanced river input. So you get increased input from both directions coming into the delta. Now this is an attempt to look at that, and so this is hours per year where the water level is above this historical 99.99% level, and there's much below atmospheric pressure, which is basically a surrogate for stormy weather. So what this is saying is these are this is how often you're going to expect to get a high sea level, high water level in the delta due to sea level and very stormy weather, implying also likely increased river input into the delta. So I want to spend the next 9 minutes talking about societal impacts, potential societal impacts of climate change. But again, this is sort of a lead-in to several of the upcoming talks in the series. Before I talk specifics, I just want to mention, to me, these are the critical issues, because these are what drive policy decisions. Policy decisions really need not to actually eliminate climate change, but they need to mitigate or prevent the harmful societal impacts of climate change. And so to have intelligent policies, we need to understand what those societal impacts are going to be. And it's also very important, I think, to understand ahead of time what those societal impacts are going to be, so that we have coping mechanisms ready when we need them. And it's important, I think, not to be in a reactive mode. So I've mentioned water supply a couple times. I'm going to just tell you the basic story on water. Many of you know it better than I do, actually. But the basic issue with water is snow. And I showed you observations indicating snowpack seems to be decreasing both in California and the West. This is a projection. And, there's a lot of uncertainty in this, but, no matter what, it's clear that the loss of snow is going to accelerate. It's going to become severe. And, it easily could be by 2050, this, like half the snow is gone. That's a lot. And the issue with that, again, is that the snow melts, and snow adds water to the reservoirs after the precipitation is ended. And this is some work by J. Lund at UC Davis. This illustrates the basic picture. And the basic picture, this is a plot of, this is actually river flow as a function of month of year. This is actually the sum of all the major rivers flowing into the Central Valley. So it's all the rivers that drain the west side of the Sierra. This is the what we call the hydrograph, the historical hydrograph. It's just a flow as a function of month of year. Interestingly, you see the peak flow is in May, and that's snowmelt. It's not precipitation. The flow in June and July, again, is snowmelt. This base flow is groundwater, and then picks up when the rain starts. Now, the colored curves are different climate change scenarios. Some of these are results of climate models. Some are simply dramatic scenarios. You can see the top one on the left. That Ringo means he's assumed a 1.5 degree change in temperature, no change in precipitation, and so on. He's got various scenarios, including increases in precipitation. And anyway, what's interesting, what you see is that we get more river flow in the winter. That's not good. That tends to increase flood risk. Can't really capture that water. That implies wasted water. We get less than historical river flow late spring and summer, and that's bad because we're depending on that inflow to keep the reservoirs full. And so this has real implications for the water supply. What's interesting to me about this is that this conclusion, you can see, is pretty robust. I mean, qualitatively, it's robust. Quantitatively, there's a lot of uncertainty. But what this is saying is that even if we get, in some cases, significant increases in overall precipitation, we still have a water supply problem. And the reason is because of warming. And the warming, again, results in more precipitation coming in the form of rain, less snow on the ground, and the snow there melts sooner. And that's why you get enhanced flows in the winter when we really don't need them. Agriculture, I'm just going to say a word about agriculture, which is, there's a lot of factors that can influence agriculture. One, obviously, is the water supply. I'm sure you all know agriculture is the biggest user of water in the state. If we have a water supply crunch, they used to tell us to put bricks in your toilet, and I used to just, because agriculture is where the water's being used. And I think, though it's not politically correct to say it, I think that's what's going to have to give. Other factors influencing agriculture are potentially pests. And this one, which is simply that a lot of crops don't like warmer weather. This is actually, again, work done by my colleague David Lobel. And he looked at projected changes in yields. These are I'm showing you 6 perennial crops. And he looked at perennial crops because they're hard to adapt, and they're hard to adapt because they're perennial. And what he's showing, I mean, there's families of curves. There's different, again, greenhouse gas emission scenarios. He's showing changes in yield, going out at the end of the century. the trends are all down. Okay, there's uncertainty and so on, but the trends are all down. And what that's saying is that these crops are actually pretty optimized for the current climate, which is not surprising. They should be. And in fact, they don't. He also showed, and I'm not showing this here, but that they wouldn't like it if it got cooler either. They're really, they're dialed into the present climate. Don't like changes. But that's an issue. Although again, it's not the only issue with agriculture. Oh, I love this. This is the extreme heat event of July 2006. Well, this was interesting to me for a number of reasons. One is it was just a shocking experience on a personal level. The temperature in my house exceeded 113 degrees for 4 days in a row, which was just, and I drove through the Central Valley. It was almost 120. I mean, it was just incredible to me. Nonetheless, actually, that heat event, in terms of the daily, the highest temperatures during the day, was not unprecedented. This slide is actually from a meteorologist at PG&E. He put it together, and what he said is, yeah, the daytime maximum temperatures, although they were new for me, were not new. Did not exceed what's in the historical record. But what made that heat event unique, and it was very impactful, what made it unique was two things. One was the high nighttime temperatures, which I showed you is consistent with the historical trend, and the other was it was the duration of the event. It lasted several days, and Woody, who is a meteorologist at PG&E, put together this graph, and this graph shows the 3-day running mean temperatures. That includes nighttime temperatures. And so every point is a 3-day running average of the temperature. This is the hottest time in the heat wave. This is the July 2006 event. These are other events in the historical record. So what he's showing is that when you look at it that way, when you look at a measure that includes several days and includes nighttime temperatures, this was a unique event. It wasn't unique. This, by the way, had real impact on 1,000 transformers exploded in 2 days. And the reason was very warm nighttime temperatures. Very warm nighttime temperatures prevented the transformers from physically cooling off, and the very warm nighttime temperatures cause a lot of people to leave their air conditioners on. Going to sleep and it's 90, 95 degrees, it's tempting to leave the air conditioner on, which is something I've never done. I didn't do it this time, but I was tempted because it's really hot at night, which is new here. So this is an example of a historical climate trend causing a particular event that's consistent with those trends and had real societal impact. And again, it was really the nighttime temperature that had societal impact. So this is just showing, not a particularly good graph, but this is actually showing projected extremes of temperature going up, up, up. And again, we haven't seen this actually in the record, but I do think it will happen. I'm just going to, this is my last real slide. I'm going to mention air quality. This is a graph of ozone, its number of days per year when ozone could be above 90 parts per billion, which is a critical threshold. And again, and this is for different emission scenarios, and this is for actually happens to be for LA. What this shows is more problems with air quality. This shouldn't surprise you. Okay, it shouldn't surprise you because you know that air quality tends to be worse on the hottest days. As it gets warmer, we're going to have more and more hot days. There's a couple of reasons behind this. One reason is, this is ozone. Ozone is produced through photochemical reactions. Those reactions require precursors. Some of those precursors are emitted naturally. Those emissions go up when it's warmer. The other factor is that the actual chemical reaction rates go a little faster when it's warmer. So for a couple of reasons, as it warms, you're going to get more ozone. And the problem with this is it really undercuts a lot of what we're doing to try to improve air quality. And in some cities, you can show even drastic reductions in anthropogenically canceled by climate change. Okay, so Terry is about to get the boat hook up, but I'm almost done. Okay, so I discussed historical trends. I showed you some, in some seasons, it seems to be that the historical warming in California is too rapid to be entirely natural. I also showed you there's kind of a lot going on in terms of different factors influencing historical temperatures. Irrigation clearly has been an important influencing factor. I made the argument that I think in the 21st century, it's going to be simpler in the sense that greenhouse warming is going to emerge as a dominant climate influence. Cooling factors like irrigation and aerosols are going to become less important. Urbanization, which is also a warming influence, I think is going to be more important. Changes in precipitation are uncertain, and I think I'm really not optimistic about narrowing that uncertainty. I did show you though that a lot of the impacts on the hydrological cycle result from warming and are pretty robust small changes in. So it would be in terms of societal impacts, I really understand what those are likely to be so that we have solutions ready if and when we need them. Okay, so that's that. I'm a minute or two late. I'll be happy to take questions. We do really, at 5 of, we're going to start rearranging the room. Yep. Yeah, sure, of course. And, well, as you know, it's not quite as simple as that. I mean, that's very controversial. We haven't had a major new reservoir in, I don't know, 25 years. I do think, we really, the other way to cope. I mean, it's interesting. It's sort of evolved, obviously. It has a lot of capacity for storing water and moving water around. To me, a key question that has not yet really been answered: can we cope with climate change and the other stressors in the water system? Can we cope with those by managing the system we have better, or do we need to build more infrastructure? And that's a perfect example of, if we're going to need more infrastructure, we better know now, because you're not going to do that in a month or a year or really 5 years. Sure. Yeah. Right. Well, that's unimpaired flows. Those are unimpaired flows. Okay. Unimpaired. Right. Yeah. Yeah. No. No. Uh, that's not correct. And yeah. 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 That's right. Although it's also true in many locations it's not significant, and the natural variability. It turns out actually the natural variability in that quantity, that center timing date, is surprisingly large. Actually, and you can imagine the factors that contribute to that. Yeah, well, along the coasts, the snow is not a factor. Okay, so you wouldn't expect this earlier shift. Or later. Roy, by the way. Yeah. Yeah. Well, I'm not an expert on that. Aside from the fact that I don't drink wine. Uh, but for one thing, this is showing quantity, and wine people care about quality. And there's been some literature claiming that changes in nighttime temperatures influence quality. But I've also heard people say, nah. So I really don't know the answer to that. Yeah. But again, this is quantity, not quality, right? And wine people, it's all about. Yeah. Yeah. Well, okay, there's some. Yeah. Yeah. So why does that happen? Okay. The short answer is I don't know, but the long answer is this is based on empirical relationships between historical climate variability and historical yield variability. And what this is showing you essentially is that in historical warm periods, yields have been worse. I don't know, I don't think the desert will warm more quickly. I think actually the desert in some way is simple because it's very dry. So you're not going to, you can get a feedback due to drying, an amplifying feedback due to drying. You're not going to see that. There's very little cloud, so you're not going to see feedbacks due to cloud. I would not expect it to be, maybe I'm missing something, but I would. Okay. So I made up a good answer. Terry knew the real answer. Okay, thanks, Terry. I know what you're saying. You just put things in the atmosphere to reflect sunlight. Well, I think it's nutty. Uh, I think it's nutty. I think, there's all kinds of problems with it. Don't get me started. But there's also, aside from just, unintended consequences, it requires cooperation. It requires a lot of effort to keep whatever it is in the atmosphere. If it's, people talk about putting particles in the atmosphere, which is really a terrible idea. I mean, they don't stay there very long. They cause all kinds of other problems. People talk about mirrors in space. It just seems dumb. By the way, and one of the actual interesting, if you look in the literature, actually, you'll see my name on some papers discussing this topic. And one of the papers shows actually that, and this is kind of interesting actually, if you block sunlight, you can't, the idea is if you block sunlight, it cancels the temperature effects of greenhouse gases, which you can do. But a little known fact actually is you cannot cancel, if you cancel a temperature effect, you actually get much less, or not much less, but you get significantly less precipitation. So you can't actually cancel the temperature effects and the precipitation effects of greenhouse gases at the same time. So if you cancel a temperature effect, you're going to get a significant reduction in precipitation, which is a problem. So that's a problem, but there's all kinds. I just think it's nutty. I don't know why people. I don't even think it's productive to really talk about it. Here I am talking about it. Okay, we have 1 minute, so let's take one question, and then we really do have to go. I'm sorry, I'd love to answer more questions. Somebody's got a question. Yeah, okay.